Good evening. This is the 11th physics class. So, do you hear my voice clearly? क्या आप मेरी आवाज सुन सकते हैं? Please write in the chat box. That's good. Okay, so any doubt or any question from last lecture, please you can type in the chat box, or you can unmute your uh, mic also, microphone. Let me share my screen. Can you see my screen now? Can you see my screen? That's good. So, I think in last lecture we covered about this coefficient of restitution. Then what is the coefficient of restitution for different stuff like head-on collision, one-dimensional head-on collision? What are the factors affecting this coefficient of restitution? And expression of final velocities after head-on elastic collision, right? We have already covered this part. Then loss of kinetic energy during perfectly inelastic head-on collision. What is the formula for that? And it is not so difficult if you know the some fundamentals like what is meant by kinetic energy. Their formula like half mv square, like v is velocity and m is mass. So from that you can carry out or you can derive the formulas. So exactly, I remember that we stopped here, right? And after this head-on collision in angle non-head, sorry, it is not like in two dimension, right? We have started and we kept it at here, and we know this formula. So and we didn't start with this example. We will start with this example now. So in this example, we are just trying to derive the formulas, and we will use these derived formulas for calculating the velocities or their masses or their kinetic energy, whatever they have asked in the problem, right? So let's see what they have asked in this problem. A shell of mass 3 kg is dropped from some height, okay, shell. After falling freely for 2 seconds, it explodes into two fragments of masses. So what's happening here? So this is one shell, and after falling up to 2 seconds, so this is 3 kg, right? And then it exploded into here after 2 seconds travel, right? Its travel is 2 seconds. They have not given us the distance, but they have given us the uh, time. So after that, it exploded into two parts. This 3 kg mass is derived into, exploded into two parts, 1 kg and 2 kg. Okay, and what they have, another information is, so basically for any problem, uh, we have to put all the information first together and try to get the information first, and from that uh, try to get the unknowns, right? So right now they have provided this information, then kinetic energy. Kinetic energy of explosion is 300 joule, right? And using G as a 10 meter per second square. Calculate the velocities of fragments. So we have to calculate the velocity of these fragments, right? I will put some different color here. So these are the fragments, right? This is a small fragment. This is a big fragment. It's 2 kg. So now what we have to do, we have to calculate the velocities. So let's go step by step. M1 plus M2. So we are considering this as M1 and M2, right? So M1 plus M2 is 3 kg. So this bigger mass is 3 kg. After falling freely for 2 seconds. So V is equal to U plus AT. So this is the formula. We know that V is the final velocity, U is the initial velocity, A is the acceleration, T is the time. So from here we can calculate the velocity at the time of explosion. So we know the initial velocity when we are dropping this shell, it didn't have any velocity, right? It has initial velocity as 0. And we know the acceleration, gravitational acceleration as 10. And T as 2 seconds, right? It fall for 2 seconds. So what is the final velocity? 20 meter per second. Now, according to conservation of linear momentum, right? Uh, we know the linear momentum equations. So m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. So what are the things here? So we know 3 into 20. So we know at this point, the velocity was 20 meter per second. Now it has been uh, divided or exploded into 2 parts. We do not know the velocity of both the particles. So we know linear momentum equation, right? So linear momentum conservation, from conservation of linear momentum, what we know that initial momentum will be the is equal to final momentum. So we know that 3 into 20 is the initial momentum, and after that it is divided into 2 parts. So 2 into v1 plus 1 into v2. V2 is this one, means second mass of velocity of second mass, and v1 is velocity of first mass. So that is 2 kg. So from here we can derive that v2 is equal to nothing but 60 minus 2v1. This is the first equation. Now kinetic energy provided is equal to final kinetic energy. So here we know kinetic energy provided is equal to final kinetic energy minus initial kinetic energy. So half m1 v1 square plus half m2 v2 square minus half m1 plus m2 u square. This formula we have derived earlier. So this is the final kinetic energy where the masses are separated into 2 different masses and 2 different velocities. And this is the combined, right? Initial combined mass. So from here, we know that kinetic energy provided is 300 joule, right? That's the information they have given. So we know the mass 1, mass 2. We do not know velocity 1 and velocity 2. And we know the u square. U square here for this part, u initial velocity is 20 meter per second, right? So already we have considered this part and we have derived this v, right? From now onwards, u will be the 20 meter per second. So don't get confused with u as a 0. Here we have used u as a 0, but for this particular example or particular problem, we are considering u as a 20 meter per second. So now here we have put all the values inside the equation. हमने सारी values equation के अंदर put कर दी हैं. And now if we derive, we derive this thing, then we will get this equation, right? 2v1 square plus v2 square is equal to 1800. But from equation 1, if we put equation 1 here, we know that v2 is equal to 60 minus 2v1. So from here, we can calculate 2v1 square plus 60 minus 2v1 V1 square is equal to 1800 if we open this bracket, and then we will get this is as a quadratic equations, V1 square minus 40 V1 plus 300. So from here, what we can do, we can carry out the quadratic equation formula. So we can use how we might have seen in earlier standards that how to calculate the values of V1 from different formulas, right? We know the x square minus bx plus c. Okay, so sometimes this type of formula is difficult to uh, take the, I mean, so how to divide this 300 into such a product of product which will so here like 300 should give something like 13 to 10, right? This is 300, and if we add up this thing, so it should come as a 40. So sometimes it is very difficult, so we can use different formulas like you might have seen in your earlier standards, that b square minus 4ac divided by 2a, right? Root of this, right? b plus minus b square minus 4ac divided by 2a. So this is the formula. This also we can use. So generally I will prefer to use this formula because sometimes it takes time to derive this 300 into two product and use that. Uh, so which addition should have the same value as this minus 40. So from here, we know the answer, like if we, there are two velocities, v1 is equal to 30 meter per second or 10 meter per second. There are two values, right? And we'll clear all the drawing. So there are two values, v1, and similarly we will get v2 is also two values. There are two possible answers since the position of two fragments can be differentiated as explained below. So if v1 is 30 and v2 is 0, lighter fragment 2 should be above. Okay. On the other hand, if v1 is 10, v2 40 meter per second, lighter fragment 2 should be below, both moving downwards. Okay. So there are two possibilities they have given because the information from which uh, we derive the equations, from that we can get two possible answers, right? So we may need more informations to fix on this v1 or v2. Okay, which is the right right combination. So sometimes we get two values, so that's fine. Okay, so this way we can solve the problem for momentum head-on sorry, explosion, right? So this is the problem of explosion, and where we use kinetic energy as well as conservation of linear momentum. If you have any doubt, please you can write in the chat box. Bullets of mass 40 gram each are fired from a machine gun at a rate of 5 per seconds. So here see bullets of mass 40 gram each. So they are using the bullets. Okay. So how many bullets they are firing? Around 5 per second. Okay. So from one machine, it's coming 5. 5 such type of things are coming from the machine. And towards a firmly fixed hard surface. So what? So it is coming to the one surface. Okay. Each bullet hits normal to the surface at 400 meter per second. So while hitting to this surface, it has velocity of 400 meter per second. And rebounds in such a way that coefficient of distribution for collision between bullet and surface is 0.75. So they have provided the information for coefficient of restitution. Okay, calculate average force and average pressure experienced by the surface due to this firing. So now what we have to calculate is the force is one, and second is pressure, because they have given the area, right? So we know formula like pressure is nothing but force by area. Okay, so just put all the information which is, so let me, I will draw it again. So this is the surface and it has velocity of 400 meter per second. Okay, so let's try to solve this problem. So what are the information given? U1, right? So we know the initial velocity 400 meter per second, and E as a coefficient of restitution, and V1 is a, we do not know, it's unknown. So for the firmly fixed hard surface, U2 and V2 is 0. So for this surface, right, there is U2 and V2. There is no initial velocity as well as final velocity because it is firmly fixed. And they have provided the E as the coefficient of restitution. So, so it's like V1 minus V2 divided by U2 minus V1, U1. So V1, V1 we do not know, right? This is unknown. So initial final velocity V2 is 0 and U2 is also 0 because it is firmly fixed. And U1 we know minus 400. So V1 is nothing but minus 300 per meter per second. So negative sign indicates that bullet rebounds in exactly opposite direction. So what does it mean? So if it is hitting in this direction, then it will rebound with 300 meter per second. So negative value indicates it is in opposite direction. Okay, so sorry, change in momentum of each bullet. So change in momentum we are trying to calculate here. So that is mass into V1 minus U1. Equal and opposite will be the momentum transferred to the surface per collision. So same momentum will be transferred to the this board, right, or hard surface. Momentum transferred per collision is P is equal to mass into U1 minus V1. So mass is 0.04 and initial velocity, so initial velocity is 400 minus 300. So we are taking the negative velocity as the final velocity, and that comes as a 28 Newton second. So this is the moment, right? The rate of collision is the same as the rate of firing. So we know the it is coming rate of collision. It's at what speed it is colliding is like number of bullets they are firing. So same rate we can use here. So momentum received by the surface per second is dp by dt, right? So we know the change in momentum is 28 and dp by dt is like it is coming in 5 per second. So we are getting 140 Newton as a total force. So this is a momentum, and if we multiply by time, so we will get force. So this must be average force experienced by the surface. So they have provided the area 10 centimeters square. So just converted it into meter square. So average pressure experienced is pressure is nothing but force by area. That is 140 divided by 10 raised to minus 3. So 1.4 into 10 raised to 5 Newton per meter square is the total pressure exerted on the firm board. Okay, so this way we can calculate the force as well as momentum whenever there are like these bullet problems. So there are certain problems which you can solve is like if this board is moving, right? So there are certain problems which you can try to solve. If this information is given, then you can try to calculate the force on this board also. Any question or any doubts, please write in the chat box. Okay, so next thing, we will start with the impulse of force. So impulse of force is like, according to Newton's first law of motion, any unbalanced force changes linear momentum of the system. Okay. Uh, we have seen that in Newton's first law of motion, any unbalanced force changes linear momentum. That is basic effect of unbalanced force is change in momentum. So what happens whenever there is a change in force, there is uh, change in momentum also. So it's basic effect of unbalanced force. So we have seen that when body is moving at certain constant velocity, right? It will keep moving in the same velocity. So we know the mass of body will remain same. So linear momentum is same for that body. Unless if we apply some force on that body, that is unbalanced force, right? So due to that, uh, it momentum changes. So there are what we are assuming, there are no frictionless surface is there, and this body is moving, right? So due to this friction, there will be change in velocity. So if we do not provide enough force, then this body will come to the rest, right? So there is change in momentum, change in velocity due to friction force or any force. So that's the same thing we have observed and we have derived in earlier discussion about first law of motion. Same principle we are using here. So according to Newton's second law of motion, now they have tried to derive those stuff like force is nothing but change in momentum. So force is nothing but change in momentum. So this force they have tried to equate with the change in momentum. So same formula we will use. So this dp is change in momentum is nothing but into uh, force into time or change in time. So the quantity change in momentum is separately named as impulse of force J. If the force is a constant and is acting for a finite and measurable time, we can write the change in momentum in a time t. So, so impulse of this force we can write in terms of this force into time. So what is the thing like main thing is we have to measure this time. If finite and measurable time, then we can calculate the momentum, right? For a given body of mass m, it becomes P2 minus P1 is equal to m V2 minus V1. That is force into time. So F is, suppose if F is not constant, but we know how it varies with the time, then we can calculate this way. So we are integrating. So what does it mean? So suppose change in momentum is nothing but simple formula we know force into time, right? So in this case, if we know the time, we can, and if we know the force, we can calculate the change in momentum. Another thing is there is another formula like mass into V2 minus V1. All right. So here, if we know mass, initial and final velocity of the particular body, then we can calculate the change in momentum as we have calculated in this example, right? So this way, what we are assuming is force is constant with the time. So if we try to derive into the graph, so force and time is on this axis. So force remains constant here with respect to time. So force is not changing. Suppose there is a force which is changing with the time, something like this. Okay, so this type of force doesn't I mean we can assume, but it's very difficult to have such type of system where force remain constant with the time. But if force is changing with respect to time, okay, so how to calculate change in momentum then? So we have to integrate. So in earlier discussion, earlier lecture also, I have described about this procedure, right? Integration. Integration is nothing but summation. So whatever this area. So what we are doing here, what we are trying to, suppose we are measuring for this time. Okay. So F into T is the area of this graph. Okay. So that's what we are trying to calculate here. Similarly, if force is changing and for particular time only, we can calculate this area, right? So there are different ways you can measure by graphical method, right? You might have studied in your earlier standard 9th or 10th that how to measure the area of such a complicated shapes. Or what we can do, we can integration. We can use integration. So if we know the F changing with the time, then we can, if we integrate this thing, then we can get this area. So that is nothing but change in momentum. So integration is nothing but, if we consider this as a graph, then the area under that curve is denoted by this integration. So if force is constant with the time, then we can just multiply F into T right here. If force is not constant with the time, then we can integrate it, right? So here what we need is function, force function. So what, like this will be something like sine of t or cos of t, anything you can observe here, right? And area under that curve, you can take it as a change in momentum. So this way we can calculate the change in momentum. So these are some notes. So colliding objects experience force along the line of impact, which changes their momentum. So colliding objects, we know that colliding object experiences force along the line of impact. So the two uh, objects when collides, so they observe the experiences force along the line of impact. So suppose this is the line of impact, right? Which, so when two colliding objects, they experiences forces. So forces are along this line of impact. Okay. For their system, these forces are internal forces. So for this system which we are considering for the force analysis, here these are the internal forces, right? These are the arrow showed in red. are the internal forces. These forces form an action and reaction pair. So here we can see that action and reaction, which are equal and opposite and act on a different object. So these forces are equal and opposite and act as a different objects, right? So this force is on from this object one, and this is from object number two. Okay, there is no forces along the common tangent. So along this common tangent, right, there is no force. In reality, the impact is followed by emission of sound and heat and occasionally light. Thus, in general, part of mechanical energy, kinetic energy is lost. So whenever this impact happens or collision happens, so there is like some energy is lost in terms of what? Heat, sound, or sometimes light. So whenever two metal objects, we might have seen in our daily example also, when two metal objects hit each other, there is small sound comes out of that, right? So sound is nothing but small energy, right? So we see that the kinetic energy is lost during this process. In reality, velocity of separation, a relative final velocity, is less than the velocity of approach, relative initial velocity, along the line of impact. Thus, coefficient of restitution is always less than 1. So velocity of separation, like final velocity. So after colliding, whatever the velocity we see, right? V2 or V1. So difference between these two is always less than the initial velocity, like U1 and U2. So velocity of separation is less than velocity of approach along the line of impact. Thus, coefficient of restitution is always less than 1. Only during elastic collision, like atomic and molecular level only, never possible in real life. So elastic collision is happens only in molecular or atomic level. So what happens there? The kinetic energy is conserved. The velocity of separation is equal to velocity of approach or the initial velocity. Okay, so this type of collision happens in if it is real big metal bodies, then it's difficult to have the E as equal to or elastic collision, right? So always E is less than 1. But in molecular level, so suppose this body 1 is one atom and 2 is another atom, and if they are colliding, so there will be always elastic collision, right? So E will be around 1. So velocity of sorry, relative uh, what happens? Kinetic energy is conserved here, and velocity of separation is equal to velocity of approach. So difference between u1 u2 and difference between v1 and v2 will be same. So that's why we can observe such type of elastic collision only in atomic or molecular level. Any question or any doubts about whatever we learned till now? Please write in the chat box, or you can unmute also, because there are not many students. So Um, I'm not sure, but if you have whether it has been covered in your mathematics lecture about derivative and integration, but derivative and integration are really important parts of physics. So please try to solve as many as problems and try to understand the fundamental behind the derivative and integration also, because it is really helpful in solving the physics. So you should know basic behind the derivatives and integration. I think in last lecture, in earlier lecture, I have discussed a bit, but if you can put your more efforts, so it will be good for you. So, okay, now necessity of defining impulse. As discussed above, we know that change in momentum is nothing but force into time. If force is constant over a given interval of time, and if we know how it varies with the time, we can calculate the corresponding change in momentum. as we have seen, like force into time, or we can integrate those stuff, right? Multiplying by force and time. So this way we can carry out the or we can calculate the change in momentum. However, in many cases, as an appreciable force acts for an extremely small interval, maybe seconds or milliseconds, right? Too small to measure the force and the time independently. So it's very difficult to measure the time. So force happens in such a fast way that we it's very difficult to measure such type of thing. So, however, change in momentum due to this force is noticeable and can be measured. This change is defined as impulse of force. Okay, so what happens that sometimes we can't measure such type of short duration forces, right? So just for an example, this is a force and this is the time. So there is no force. So it is, we can assume it as zero. So okay, so I will take it as a zero, right? There is no force. Suddenly there will be force, and it will be for very short duration, right? So this happens. This type of phenomena we will see just now. So so this is, and we can't measure such type of thing, but we can measure the impulse of force. The what happens after that we can measure. So the real life illustrations, let's see, hitting a ball with a bat. So we know that if we hit the ball with a bat, it's very far. That bat and ball duration is very small, right? But we know that ball travels a lot after hitting to the bat. Giving a kick a football. So same, like if we kick to the football, we know that it will travel, but that kick, so that impact happens to this ball is for very short duration. Then hammering a nail, we know that if this is a nail and if we are hammering this hammer, uh, right? So whenever this hammer strikes on this nail, so this nail moves in this direction, right? And if we are hitting in this direction, so that impact is for very short duration, hardly we can measure. Then bouncing a ball from a hard surface, right? That is appreciable amount of force is being exerted, but it is very difficult to measure for the short duration. In such cases, the time for which these forces act on respective object is negligibly small, right? Very for small duration, we are hitting to the ball with a bat, or we are hitting to the football with a kick, or we are hammering a nail, right? It's for very small duration and mostly not easily recordable. It's not like we can't record, but it's very difficult to record, right? So however, the effect of this force is recordable. So we know the effect of such forces, like suppose if we use this hammering, right? We know that nail will move from this distance to this distance. This is recordable, right? If we measure the initial position of this nail and final position after hitting that hammer, we know this position. Or similarly for this kicking to the football, right? We know the initial velocity is zero, but where it is traveling, right? Its velocity and distance it's travel, we can measure those stuff. So we know the force applied by the person on kicking this football. Similarly for bat and ball, which we use for the cricket, right? Here also, how the ball is traveling, cricket ball, we can measure. Or bouncing a ball also, similarly, how much that ball is bouncing from the hard surface. So that also we can measure the distance. So this way, effect of this force we are measuring, we are not measuring directly force. So thus it is convenient to define the change in momentum. In such cases, the time of okay. So this is convenient to define the change in momentum itself as a physical quantity. Sorry. So we can see in the graph also, right? So here hardly any force. Then for very small duration, there is force, right? And then afterwards again it is zero. So this type of impulse happens, right? Impulse of force. So this is the variation of force as a function of time. For a collision between bat and ball with a force exerting starting with zero, right? Force exerting starting with zero, the shaded area under the curve gives the product of force against corresponding time. So this area gives us force into time, hence gives an impulse. For a constant force, it is obviously a rectangle. We have seen that if it is constant force, but it is not constant. We know that we hit to the ball, then again this force is coming to the zero. Rises to maximum and decreases to zero after the impact. After the impact, it becomes zero. For a softer tennis ball, the collision time is larger and the maximum force is less. So what happens for softer tennis ball? The collision time is larger. Why? Because that ball gets deformed, right? So we see that there is more time while impacting. So maximum force is less. So we may not see the more force, but yeah, there will be the time at which it is contacting will be the more. The area under FT graph is the same. So we know that if we hit to the tennis ball, we or if we hit a very hard ball of cricket ball, right? So this way we know that the force is same. Wicketkeeper ages off by increasing the time of collision while catching a fast ball. So what wicketkeeper this does for fast ball, what it does by increasing the time of collision. So what they do, they increase the time of collision, right? So they keep in their gloves itself. So that is like more contact time. So that way they ease off to make the energy less impacting to them. As I mentioned earlier, so what does it mean that so this force happens, right? So either what we can do, we know that energy is same, either it's ball, traveling ball, or anything, right? So if we want to, this is the same, right? This area will remain same. So either we can increase this time so that impact of force will be less, right? Like for the softer balls. So how to increase the time? So we use like we know that for softer balls, we can increase the time of contact while the force is applied. So this way, wicketkeeper also does same thing by increasing the time of collision while catching a fast ball. So there will be, you know, less impact of force. So as I mentioned, it is absolutely necessary that the force axis must start from the zero. Force axis must start from the zero. Recall from chapter 3, analogous concept using the area under curve are obtaining a displacement in a given time interval as area under curve for VT graph. So in chapter 3, you might have seen that how displacement is nothing but area under curve of velocity and t. So this is velocity and t, and velocity is this, then this area under curve gives us displacement with zero origin, right? Similar type of concept we have to use here also, obtaining the energy or impulse. So what we are trying to measure here is impulse, F into T, force into time. Obtaining work done by force as the area under the curve Fs graph with a zero origin for a force axis. So similarly, we are trying to do same thing here. Sorry. So let's try to solve some problem that this thing will be more clear. So mass of an oxygen molecule is around 5.35 10 raised to minus 26 kg, and that of nitrogen molecule is 4.6 10 raised to minus 26 kg during the Brownian motion. So what happens that in air, we know that if oxygen molecule is there, these are the oxygen molecules, right? They will try to go here and there, and they are not constantly at the same place, right? So these molecules are nothing but, I mean, these molecules travel here and there. So it is called as Brownian motion. इसको Brownian motion कहते हैं. So oxygen molecule is traveling with a velocity of 400 meter per second. Collides. So this is oxygen. Okay. And there is another molecules that are nitrogen. They're also traveling here and there. So we are now particularly considering only one molecule where the it collides with a nitrogen molecule, right? So this will collide with the nitrogen molecule, and that is elastic collision, right? Elastically. Molecule traveling with a velocity of 500 meter per second in exactly opposite direction. So we will take only one molecule here out of this so many molecules, right? And try to consider the system. So this is O2 and this is N2. So what is happening here? Uh, this is traveling with 500 meter per second, but in the opposite direction, right? And this molecule is traveling with 400 meter per second. Calculate the impulse received by each of them during collision, assuming that the collision lasts for 1 milliseconds only. How much is the average force experienced by each molecule? So we will try to calculate first is mass, M1. We'll take it as a one, body number one, and M2 as a second body. So we know the mass, right? U1 for each object or each body is like U1 is 400 meter per second for oxygen and U2 is minus 500. Taking direction of motion for oxygen molecule as a positive direction, right? We are considering this as a positive direction. Hence, this velocity for nitrogen comes as a negative 500. For an elastic collision, V1 is equal to M1 minus M2 divided by M1 plus M2 into U1 plus 2M2 divided by M1 plus M2 and U2. For elastic collision, we have derived this formula, right? Similarly for V2 also. So we know this formula. We have derived in earlier discussion. So from here, we can calculate V1 and V2 because we know U1, M1, M2. So all are known. From that, we can calculate the V1. So for impulse on oxygen is MO V1 minus V1, that is minus 4.478 into 10 raised to minus 23 Newton second. Similarly, for impulse on nitrogen molecule is nothing but final velocity minus initial velocity into mass. That's we know we have calculated through the formula like mass into change in velocity is nothing but change in momentum. So that is around plus 4 point. So we can see that so on J momentum on oxygen is minus and momentum on nitrogen is positive. This is due to direction only. As expected, the net impulse or net change is in momentum is zero, right? Net momentum change is zero. So we are not losing any momentum here and there. And we know that from linear conservation of linear momentum, momentum before and after remain same. So F0n, so force which happening between this while colliding this between two molecules is nothing but impulse divided by time, right? Change in momentum with respect to time is nothing but force. So this is the change in momentum we have calculated. Now we have to calculate the force. So they have provided the time for which it happens, that is 1 millisecond, right? So each millisecond there is collision is happening. That's what it means. So for each time, so 10 raised to minus 3 is time. So momentum we have calculated divided by time gives us the force. Okay, so from here we know the force. So this is the force which is acting on these molecules. 4.478. Let me clear all the drawing. So 4.478 into 10 raised to minus 20 Newton. So we can consider this as means you might be knowing this thing, but just I want to repeat it. So 4 divided by 10 is nothing but 4 into 10 raised to minus 1. Similarly, 4 divided by 100 goes to 4 into 10 raised to minus 2, right? So similarly, if we go, so it is nothing but 4 divided by 1 into such a 20 zeros, right? That gives us this type of force. So 4 divided by 10 raised to 20. So it is so small force. It's very, very difficult to measure, right? And then for such a short time. So just I wanted to give an uh, what is the range of force. So if we take the 1 kg mass, we know if we go to any shop, we can take 1 kg dal or 1 kg rice. So that 1 kg is nothing but equivalent, okay, is nothing but equivalent to 10 Newton force, right? That is 10 Newton. And this force is nothing but 4 divided by 10 raised to 20. So such a small force, right? So at a molecular level, such type of small forces, we have to play with such a small forces or small distances. Okay. So let me know if you have any question or any doubts, whatever we learned till now, or if you want to change something, or if you have any doubt from the problems given below the chapter, we can discuss that too. If you have any questions, I'm not covering those questions because the theory is such a large context here. So if you have any question about those problems also, we can discuss here in the class. Okay. Now, till now, okay, if you do not have any questions, then we can go ahead. So we will see that now rotational analog. So what is meant by rotational analog for the momentum force or torque is like, till now we were thinking of straight force, but there are some forces while rotating also. So those type of stuff we will discuss here. So while opening a door, okay, we know that door is there. So if we see from the top, right? So this is the hinge and this is the door. So this we open. We are seeing from the top. Okay. So this type of door we can see, or if I take this as a three-dimensional, so we know that this is the door, right? And we can open this way. So what happens? We apply force away from the hinges. So these are the hinges and we apply force. This is the top view we can see. So from hinges, it opens, right? And we apply the force perpendicular to door, right? We apply force in this direction and it opens. In this case, we are interested in achieving some angular displacement for a door. So we see the angular displacement, right? So this is the angular displacement. If the force is applied near the hinges or nearly parallel to the door, it is very difficult to open the door. So try it at your home or anywhere. Uh, Now you are opening door from here, right? Try to put force here. and try to open it, you may need more force. Okay. Or if we use some parallel force, so it will not open, right? It will slide over the door, but it will be difficult for open this such type of doors, right? So it is very difficult to open that. Similarly, if the door is heavier, made of iron instead of wood or plastic, we need to apply proportionally large force. If this door is made of iron or steel, then yeah, we may have to put larger force. So what does it shows? It shows that there is something different stuff we have to consider, or we have to deal with. It shows that rotational ability of force not only depends upon the mass, right? So rotational ability here, it's not dependent only on mass, right? But also depends on point of application of force. The point should be as away as possible from the axis of rotation. So in this door example, we know that instead of applying force here near to this axis, right? This is the axis of rotation. We should apply force here, right? Because so the point should be as away as possible from the axis of rotation, and the angle between direction of the force and the line joining the axis of rotation with the point of application effect is maximum if the angle is 90 degree. So what does it mean? So this is the application of force right here. So this force should be the 90 degree to this line which is passing through this axis of rotation. Okay. So then only you will feel that effect is maximum, means you can open door very easily. If you change this angle of this force from 90 degree, this 90 degree, right? And from 90 degree to 30 degree or 40 degree, you may have to put more force to open the same angle of door. So these are all the physics. Taking into account of all these factors, the quantity moment of force or torque is defined as. So what is meant by torque? So this is moment of force. This is not momentum. Okay, so you have to be very careful about what is meant by moment of force. So this is moment, right? Happening, or torque. We can simply call it as torque, defined as a rotational analog of force. So till now we were defining the force only, right? That is what was unit Newton. But here we are dealing with the torque or moment of force. As rotation referred to direction, sense of rotation, torque must be a vector quantity. So similarly, here also we are dealing with the direction. Direction is important for the torque. So that is also vector quantity. It is mathematically form. We can define as a torque or moment of force is nothing but radius position vector into force. So that is torque. So torque is nothing but, so suppose this is the body, if we are, and this is the hinge along which it rotates. So this is the axis, right? So we know the simply we can take it as an example of our fan, right? So this is the ceiling fans or table fans also. Table fans are different blades, shapes. So in these fans, we know this is the axis of rotation here. So this goes into the paper, right? So this is the axis of rotation here. And these are the blades, right? So if we want to calculate the torque, we can calculate through torque, nothing but radius from this, or radius or position from the axis of rotation, and force which we are applying. Okay, so this is the torque. We have just introduced the new term, torque. We will we will discuss more in the next lecture. Thank you. See you in next lecture. Have a great evening.